Welcome to MS 100 lessons, and in this lesson I will be discussing the normal force. I will state out the definition of the normal force and I will show you how to calculate the normal force from a free body diagram. Okay, so for me to explain what a normal force is, I will use an example. Let's say you have a surface or you have a table surface up here, and then on top of this table you place an object of mass m, right? So the fact that the table is not breaking when you place this object on the table, it is because there is a reaction force that the table exerts on the object. Okay, so the surface of the table will exert a force on this object, right? But before that, this object has a mass of magnitude m, right? So it means it has a gravitational force which is acting downwards, right? So when you place this box on top of this table, right, and the box remains on top of the table, right, it means the table exerts a reaction force to the box, right, in that direction. So this force will balance the gravitational force in this case, right? So the normal force is exerted by this surface of the table to balance the gravitational force. That is why the box can stand still on top of the table. Okay, so now what happens if, in this case, the fact that it is stationary, right, and there are only two forces, we can see that the normal force is equal to your gravitational force, right? So what happens if your gravitational force becomes greater than the normal force? Okay, so it means now the table cannot balance the gravitational force because the gravitational force is greater than the normal force in this scenario. Okay, so if the gravitational force is greater than the normal force, in this case it means the table will break. Okay, it will break and this object will continue moving downwards. Okay, that is because the gravitational force of that object is greater than the normal force of that is exerted by the table on the object. Okay, so by definition, what is a normal force? So a normal force, it is a force which is exerted by the surface on an object. Okay, but for the table to exert a force on this object, the object and the table must be in contact. Okay, so that is why we say normal force is a contact force, because without contact there is no force acting. Okay, so this is a force exerted by a surface on an object in contact with the surface. Okay, so as you can see from the force diagram that I've drawn here, the normal force is perpendicular to the surface. Okay, so it always acts perpendicular to the surface. So normal force is the force exerted by the surface on an object in contact with the surface. Okay, so the object must be in contact with the surface, and this force acts perpendicular to the surface. Okay, so that is your normal force. So now I want to check how do we actually calculate the normal force, right? You calculate your normal force using your F net in the y direction. Okay, so let us look at these three scenarios. We have scenario number one, whereby say we have an object which is moving to the right on a rough surface. Okay, so now scenario number two, we also have an object which is moving to the right on a rough surface, and also scenario number three, we have an object moving to the right on a rough surface. Okay, so the question is calculate the normal force in each scenario. So for you to calculate the normal force, you always follow the steps of analysis, right? And remember step number one, from our Newton's laws, we have separate, and there's no need to separate because there's only one object in this case, right? And step number two, you draw your free body diagram. So let us draw the free body diagrams for each. So the free body diagram for the first scenario, we have the applied force, which is to the right. Since we have mass m, we have gravitational force going downwards, right? And since we have a surface, we will have a normal force which will act perpendicular to the surface. And since we have a rough surface, then we will have friction. Okay, so now the free body diagram for this object would be gravitational force, normal force upward, applied force, and kinetic friction, right? So how do you calculate your normal force in this case? Your normal force, you calculate your normal force with F net in the y axis. But remember our steps of our analysis that we used. We say step number one, you separate the objects, right? But in this case, there's only one object. There's no need to separate the objects. Step number two, you draw your free body diagram. You have drawn your free body diagram, right? Step number three, you resolve any forces that you need to be resolved. In this case, we have normal force in Fg in the y direction, and we have applied force and kinetic friction in the x direction. So there's no force that we will have to resolve. Okay, so let us go to step number four, which is F net in the y-axis. F net equals to ma in the y-axis, right? So how many forces do we have in the y-axis? We have two forces. We have the normal force and we have Fg. Okay, so normal force is positive because it is pointing upwards, right? Because we choose our system of axis to be upward as positive and downwards as negative. Okay, so in this case the normal force will be positive and Fg would be negative. That is equal to the mass of the object multiplied by the acceleration. But the objects are not moving in the y direction, so acceleration in the y axis or in the y direction is equal to 0. So the normal force minus Fg is equal to 0. So the normal force in this case is equal to Fg, right? So now we have the normal force being equal to Fg. So that is how we calculate our normal force for the first scenario. And Fg, you can calculate Fg by saying Fg is equal to mg, right? Okay, so my normal force is equal to Fg, which is mg for the first scenario. So let us go to the second scenario now. Let us calculate our normal force now. So step number one, you separate. There is no need to separate because there's only one object. Step number two, you draw a free body diagram. So let us draw the free body diagram for this object. So we will have our gravitational force, since we have mass, pointing downwards, okay? And then we will have our normal force, right? Pointing upward, which is perpendicular to the surface, right? So that is our normal force because we have a surface. And since we have a rough surface, we will have kinetic friction in that direction, okay? And we also have our applied force, which is applied at an angle, okay? Our applied force is applied at an angle theta. So now that this was step number 2, right? Let me just write down the steps just to remind you of the steps that we have to follow. Step number 1, I said we separate, okay? And step number 2, we draw a free body diagram. Step number 3, you resolve, okay? Step number 4, F net in the y-axis. Step number 5, F net in the x-axis. And step number 6, you solve, right? But now we are only following these steps because we want to calculate our normal force, right? So we have done step number 2, which is the free body diagram. So now we have to resolve our free body diagram. So as you can see, we have our system of axes to be positive x-axis and negative x-axis that side, right? Positive y upward, negative y downwards. So in this case, you can see that normal force is in the y direction. There's no need to resolve normal force. Fk is in the negative x-axis, so there's no need to resolve it because it is in the x-axis, right? And then Fg is in the y-axis, there's no need to resolve it. But if you can check the applied force is applied at an angle, theta, right? So we have to resolve this force into 2 components, right? So when we resolve the force into 2 components, we will have the x component and the y component. So that is Fa x and Fa y, right? So since we have shown Fa in terms of components, we can remove that Fa, right? And our calculation for Fa y would be F sine theta, and Fax would be F cos theta. Okay, so we have resolved now. So the next step after resolving, we have F net in the y-axis so that we can get our normal force, right? So F net in the y-axis, that would be F net equals to MA. And how many forces do we have acting now on the y-axis? From our resolved free body diagram, we can see that we have Fg, we have Fay, and we have the normal force, which means we have 3 forces, right? So we have normal force, which is positive because it is pointing upward, right? And we have Fay, which is positive. So plus Fay, which is positive, pointing upward, and we have Fg pointing downward, right? So this is equal to the mass of the object multiplied by acceleration. But acceleration, this object is not moving in the y direction. So it means acceleration in the y direction is equal to 0. Okay, so that would be 0, and normal force plus Fa y minus Fg is equal to 0. So let us calculate the normal force. The normal force would be, if I take Fg to the right hand side, that would be positive Fg, and if I take Fay to the right hand side, that would be negative Fay. Okay, so now as you can see that my normal force now is not equals to weight, right? But my normal force is equals to Fg minus Fay, right? And that is equals to Fg is mg, okay, minus Fay, we said that is F, which is our applied force, sine theta. Okay, so if you can see, or if you can compare the two normal force which was obtained in scenario number 1 and normal force which was obtained in scenario number 2, the normal force in scenario number 2 is actually less compared to that of scenario number 1, because you can see that that is mg, okay, that is mg, but this is mg minus something. Okay, we are subtracting something from that mg, so we will get a lesser value for the normal force in scenario number 2. Okay, so if we can have a question to say, is normal force always equals to gravitational force? Is normal force always always equal to gravitational force? The answer is no, right? Because you can see in the second scenario that the normal force is not equal to the gravitational force, but it is equal to the gravitational force minus Fay, the component, the y component of the applied force. Okay, so why is the normal force a bit less compared to that one in scenario number 1? This is because the y component of the applied force is actually lifting the object up, and as it lifts the object up, it decreases the contact, right, between the surface and the object, and the normal force actually decreases. Okay, so let us look at scenario number 3. Let's calculate the normal force in scenario number 3. Okay, so for scenario number 3, step number 1 is separate. There is no need to separate because there's only one object, right? Step number 2, you draw your free body diagram. So let us draw the free body diagram here. So the free body diagram for step number 2, for scenario number 3, we will have our Fg, which is downward because we have mass, okay? And we will have our normal force, which is upward, perpendicular to the surface. And we will have our friction, which is Fk, right? And we have our applied force in that direction. Okay, so the applied force is applied theta degrees from clockwise from the positive x-axis. Okay, so the next step now is to resolve this free body diagram. Okay, so when you resolve this free body diagram, you will have two components of the applied force. You will have that component which is Fax, right, and the y component which is Fay. So now you can remove that applied force since you have represented it using the components, right? And by calculation, Fax would be F cos theta and Fay would be F sine theta. Okay, so now we have completed step number 3, which is resolving. So now let us go to step number 4, which is F net in the y-axis, so that we can calculate our normal force. So F net in the y-axis would be F net equals to MA. Okay, how many forces are in the y direction? In this case, from the resolved free body diagram, we can see that there are 3. We have the normal force, we have Fg, and the component of the applied force, which is Fay. Okay, so we have the normal force, which is positive. We have Fg, which is negative since it is pointing downwards. We have Fay, which is negative, which is pointing downwards, right? That is equal to the mass of the object multiplied by the acceleration, and since they are not moving in the y direction, the acceleration is equal to 0. Okay, so that would be normal force minus Fg minus Fay equals to 0. So my normal force is equal to Fg, right, plus Fay. Okay, so you can see now that the normal force in this situation it is equal to the gravitational force plus the component of the applied force, the y component of the applied force. That would be mg plus f sine theta. You can see now that the applied force is the greatest not the applied force. The normal force is the greatest compared to the three scenarios, right? Because the first one, the normal force is equals to mg, okay? And for the second one, the normal force is equals to mg minus the component, the y component of the applied force, so we get a lesser value. But for the last one, we have normal force being equal to the Fg plus the y component, and this is a greater value, right? So why do we get a greater normal force when we have an applied force which is applied in that manner? This is because the y component of the applied force is actually pushing the object downwards, okay? And as it pushes the object downwards, it increases the contact between the object and the surface, right? And as it increases the contact, the normal force increases. So that is why we are getting a greater value for the normal force for the last scenario. So just note that the normal force is not always equal to Fg, right? You always have to calculate your normal force using the steps that we follow to analyze these kind of questions. So now let us look at the normal force at an inclined plane. Okay, so suppose we have a surface which is inclined at that angle, theta, okay? And we have an object of mass m sliding down the incline. Okay, let's say it is sliding on a rough surface. All right, so now we want to calculate our normal force for this object, right? So first of all, we first have to follow the steps of analysis, which is separate free body diagram, we resolve, and we obtain our F net in the y direction. So now we have an inclined plane, so the normal force now would be equal to the component of Fg. Okay, so let us illustrate that using this free body diagram. So we have Fg, which is acting downwards, okay, and we have, since the object is sliding down the incline on a rough surface, then it means we have Fk acting up the incline, and remember we have a surface here, right? And there is a reaction force which we call the normal force, which is perpendicular to the surface in that direction. So we have our normal force in that direction. Okay, so now that was step number 2, which was drawing the free body diagram. So step number 3, we resolve any forces which is not in the system of axis. So remember, when when it is an inclined plane like this, the system of axis that we use that x-axis and that y-axis, right? And you can see that normal force is in the y direction, Fk is in the x direction, okay, but Fg is not in the x and it is not in the y. So we have to resolve this into components, right? So when we resolve this Fg, we will have two components, which is the Fg parallel and Fg perpendicular, right? So now we can remove that Fg. So now we have resolved the free body diagram, or we have resolved weight. So now let's move to the next step, which is F net in the y direction, right? So that we can calculate the normal force. So F net in the y direction, that would be F net equals to MA, okay? And how many forces do we have acting in the y direction? We have two forces. We have the normal force and Fg perpendicular. And from our resolving, Fg perpendicular should be equals to mg cos theta, and Fg parallel, that is mg sin theta. Okay, so F net in the y-axis, we have the normal force, which is positive, and we have Fg perpendicular, which is negative. That is equal to the mass of the object multiplied by the acceleration. But the acceleration now, these objects are not, or this object is not moving in the y direction. So it means the acceleration in the y direction is equal to 0. So that is the normal force minus Fg perpendicular equals to 0. And the normal force is equal to Fg perpendicular, right? And that Fg perpendicular is equal to mg cos theta. So now you can see that your normal force is equal to the perpendicular component of weight, okay? And it is not equal to the weight, but the perpendicular component of the weight. So we can also conclude here that the normal force is not always equal to the gravitational force. Here it is equal to the gravitational force minus the y component. Here it is equal to the gravitational force plus a y component of the applied force. And in an inclined plane, we can see that the normal force in this case, for this scenario, we have normal force being equal to the perpendicular component of gravitational force.